Hello everyone, welcome to this week's tectonics lecture. The topic for this week is going to be elastic flexure of the lithosphere. So this is a subfield of isostasy, and I'd like to go through a little bit of the theory of this and why this is important to many geological processes, including tectonic processes such as mountain building and the isostatic reaction to that. So I think everyone has seen local isostatic compensation at some point or another. This is simply the argument that through, change pointers, that simply through the vertical loading and then the rebound force through buoyancy from the asthenosphere, a load will find its natural balanced elevation somehow floating in the asthenosphere. And that load could be things like changes in crustal thickness, but it could also be things like ice sheets on top of the lithosphere. But this is an approximation. This is an approximation to what really happens in the Earth, which is that this kind of a load is supported by the strength of the lithosphere. So this depends then on the rheology of the lithosphere. But if the lithosphere is stronger than the asthenosphere, as we believe it is, then it will partially support this load before we ever suppress the base of the lithosphere and induce buoyancy reactions here. Furthermore, it will distribute the load over a much broader region. And if this deformation, this support is done elastically, we end up with what we refer to then as elastic flexure of the lithosphere. This is illustrated very nicely in several settings in the oceans, which I'll focus on today's talk. We'll go more to the continents next in the next video. But we see that, for example, in trenches. What is a trench? A trench is really where the oceanic lithosphere is bent down before it gets subducted underneath an overriding plate. And that bending is in fact a type of elastic deformation. And if we look at the profile of across any ridge, any trench really, if we go across a trench and look at the topographic or bathymetric profile, what we'll see is that, yes, here's the trench. It goes down into the trench, but as it comes out of the trench, it actually overshoots and it goes a little bit too high, and then it goes back down again before it goes out to the sort of equilibrium ocean floor water depth. And we see that pretty universally. Almost everywhere you look at a trench, you'll find what's now referred to as an outer high or a trench bulge, or in this case, it's a rise, the Hokkaido rise. And this is thought to be then some kind of a flexural response that says that this bending as the plate goes down is not a pure permanent deformation like one would get with a viscous bending, but it is an elastic bending that's forcing the plate to take a particular shape that's consistent with the strength and thickness of that plate. So this kind of a problem of a elastic bending of a plate has been looked at in the engineering literature for many decades. It's very well known because, of course, if you have something like a steel beam or a steel plate and you apply a load, the engineers would like to know how far it will bend, how much will it bend, and how far will it bend, say, before it fails. So we need to be able to predict the stresses inside a plate and also the degree of deflection that occurs under a given load. So this problem, in fact, has been simplified. So the simplification is to a plate, to a thin plate, where it's argued that in fact, even though the load is here vertical, the stresses are going to respond only in the horizontal direction. And the reason they do this is because the stresses are dominated by a bending or flexure of that plate rather than, say, by the vertical loading. Normally, if you put a load on a solid, you'd think, most of the stresses are going to be directed downward, right? We have a sigma Z that's pushing down on the plate. But in fact, if that push leads to a deflection, and this is going to be called W throughout the next few slides, a deflection W, then in fact that induces this flexure or bending in the plate, and that induces horizontal stresses. And in fact, those horizontal stresses, if we go straight down directly underneath the load and blow it up a little bit, we get this picture. Those horizontal stresses look like this. They're horizontally compressive in the upper part of the plate, and they're horizontally extensive or tensional in the bottom part of the plate. And in fact, there's a point in the middle of the plate that's called the neutral fiber, where these bending stresses are zero. There is no stress. And this sort of makes sense if you think about it, that if you bend a plate like this, the top part is going to be compressed because it's getting bent inward, and the bottom is going to be stretched out because it's getting pulled outward. And that's what this is. And what makes this a plate, or a thin plate, and defines this flexure then is that these what we call fiber stresses, these horizontal stresses, are assumed to be the only thing that matters. So how do we go about then calculating what these stresses are? These, by the way, I have an extra slide in here, so I'm going to leave it in. I don't know why this one was double and I have one green line, but just ignore this. And I'm not going to take it out in the PDF because it's going to change the numbering. So the numbers down here are going to stay the same. And we have one slide in there twice. All right, so how do we calculate these stresses and these deflections? Well, these depend on the elastic properties of the plate. The elastic properties, like any elastic body, are pretty well understood. We know pretty well how to define these. These now are for a solid three-dimensional body, though, so it's not going to be as simple as our old spring constants that you may have seen in other classes, right? We do have to worry about how things work in 2 or 3 dimensions here. So the first elastic modulus that's important is what's called Young's modulus. And this is simply the physical characteristic, physical property of a material that defines the proportionality between stress and strain. And this is in terms of a longitudinal strain and a stress, and a normal stress in the direction which we're calculating, right? So if we apply a stress and we look at how much that strains a body, depending on Young's modulus, you'll either get a large strain or a small strain. So Young's modulus is defined here, and that's defined then as the ratio between the stress and the strain in this direction. There's also a shear modulus that acts equivalently, but for a shear stress. So if we apply a force, a shear stress or shear force to a body, we can look at how much the deflection is in terms of an angle, define that angle in terms of a shear strain. And if we look at the proportionality between a shear stress, say tau, and the shear strain, this gamma, that proportionality is called the shear modulus. So that gives us a second characteristic of an elastic body. How many characteristics do we need? Well, we need at least 2, as it turns out. That if you look at the full 3-dimensional problem of elasticity, we have to worry about, and I hope you've seen this before, but I hope you know that in a 3-dimensional body, there are in fact 6 independent components of stress. So there are the 3 normal components, XX, YY, and ZZ, and then we have the shear components, YZ, Z, X, and XY. In fact, there's really 9 components, but because of symmetry, 3 of those disappear, and we have 6 independent components. And the same is true for strain. We have to worry about those as well. So a proper description of elasticity, and if it's isotropic, that's the simplest way, but in the simplest form, we need to know, in fact, at least 2 and potentially 3, depending on how you want to define it, of these elastic moduli. And this is now called the compliance matrix, which in fact relates then to the stress and the strain in 3 dimensions, right? So there are other elastic moduli then that we might have to worry about. Lamé modulus is one, the Poisson ratio is another, and then the bulk modulus, which just comes into compressible materials. But it turns out there's kind of relationships between all of these. So if you want to look, for example, at the shear modulus, you can actually relate that to the Young's modulus and Poisson's ratio. So in fact, if we took this definition of G, fed it back in here, we could reduce this back down to 2 elastic moduli, but you always need to know at least 2 of the elastic moduli and then define the third in terms of the other 2. And in fact, there are all these relationships between all 5 of these elastic moduli. So if you have your favorite and you want to express things in terms of any particular 2, then you can redefine the others in terms of these. It's just a kind of for your reference, a complete reference to how all these elastic moduli relate to one another. And you can look this up lots of places on the web, like in Wikiversity here. All right, so what do we need for an elastic plate? So for an elastic plate, it turns out that we can write this force balance in terms of vertical force applied to the plate and a flexure of that plate, where again W now is the deflection of the plate, and to write this out properly, now we end up with 4 derivatives of the flexure times d, which I'll come to in a moment, plus 4 derivatives of the deflection. And then we have a restoring force. This is a buoyancy term, which is the same as we have in isostasy. We can ignore this one for a moment. That's if you want to load the plate horizontally as well as vertically. So what this is saying, and these are just the densities. So this is actually the density of the fluid that fills that's above the plate, and the density of the fluid that's below the plate. So if the load is sediment, for example, we're filling it all with sediment. The D here is the important physical property. And this is, in fact, what defines how much deflection there is for a given force. This is what's called the flexural rigidity of a plate, and that's expressed down here, D flexural rigidity. And this D is a function of the elastic moduli. So here's Young's modulus, and the Poisson ratio is here. And so this is where the elasticity and the material properties come in, but there's a third term here, which is this TE. That's the thickness of the lithosphere. All right, so that's down here, thickness of the lithosphere in meters. All right, so by looking at the thickness and the elastic moduli, we can then define how much flexure a plate is going to exhibit in response to a given load. And we're going to look at a few of those solutions to this kind of problem right now. The other thing we have to define is what our boundary conditions are for a plate. And in most of earth science, there's kind of 2 problems that we look at commonly. One is what we call a broken plate, where what that really refers to is the fact that one end of the plate is freely hanging down into the asthenosphere. So this would be the trench case, for example, an oceanic slab, where that slab is now dangling down here. If this is the end of it, then there are no stresses on the end of the plate here. The other one is if we have a continuous plate. So this would be the case if we had the entire lithosphere with a load that somehow plopped down on top of the plate. Maybe it's a volcano or an ice sheet or something like this, but the plate itself is undeformed, or not, well, it's not unbroken, and therefore behaves relatively continuously. Okay, so we'll have to look at each of these cases a little bit separately. So let's start with the case of a continuous plate that is subjected to a line load. Now, by a line load, I mean that the load is applied in this picture at a point, but in fact, the load extends in and out of the picture of the screen right here infinitely. So it is truly a plate, but it's symmetric in and out of the board or in and out of your screen. So in fact, it looks like it's a single point in all these pictures. So we make a couple of assumptions. We assume that the plate is elastic. It's not rigid, but solid, that should say, really. And it has a linear elastic rheology, one-dimensional in this view, and it's thin. So the thickness of the plate is small compared to the size, and the deflections are small. We have to make these assumptions or the problem is no longer a thin plate. The plate is supported then by an asthenosphere, which has some buoyancy, fluid buoyancy term that comes into the problem then. What does a line load look like? Well, it looks like things like this. This is the Hawaiian Emperor Seamount chain. So this is a hotspot mountain chain or volcanic chain. This is the active volcano of Hawaii today, but there's this long string of older volcanoes like this. If these volcanoes are acting like a surface load on the surface of the oceanic lithosphere, we can approximate that as an infinite line by, say, taking a profile here where these blue arrows are around Kauai and simply ignoring the fact that it's got an end here and a turn here and say this is effectively an infinite line, and we're going to look at that line load on the lithosphere right here. Okay, so if we do that, what we find is that we can we can solve that fourth order differential equation that I showed you a few slides back. And the solution to that is right here. You can go back and check that if you want. But what this is saying then is we have a deflection that's a function of x. And it's a function here, here it's going to be expressed not in terms of a load, but in terms of a maximum deflection. That maximum deflection that occurs right here, however, can be related to the load that's down here. So if we apply a load of V0, this is a force that's being applied now. We have, again, these rebound terms, and that gives the maximum deflection, which comes in here. There's one term to the solution here, which is this alpha. That alpha is in fact called, or it's referred to as the flexural parameter. Don't mix up flexural parameter with flexural rigidity. The flexural parameter is a function of the flexural rigidity, D, and also the rebound force, which comes in as this delta rho. Okay, so the delta rho, again, is the density of the material down here and the density of the material above. This is a cosine sine function with an exponential, which means that it damps out as you get further and further away from the load. And the shape of this is right here. This is now, unlike, you know, these little sketches, this is the true solution to a continuous plate under a line load. It goes deep, comes up. We have this flexural bulge that comes up above the datum, then it goes back down again. It's only plotted to here, but in fact, it oscillates a few more times infinitely. It's a sine cosine function, but the amplitude gets smaller and smaller because of the first term. So we typically ignore everything from about here outward. So it has a crossover point that comes in. We could define that as x0, and a second crossover point that is, or sorry, not a crossover, but it has a maximum, which we could define as xb. And we can solve those as part of the solution. Those occur at a fraction of alpha. So in fact, the high point of the flexural bulge occurs right at a value of pi times alpha. This is why alpha is useful. If you calculate alpha, it tells you exactly where the flexural bulge will be with respect to the load here. And the 0 point, so if we had, for example, a sedimentary basin at sea level, this would be the filling of the basin would occur right at a value of x0, which we can also calculate as 3 pi over 4 times alpha. We can calculate other things like the height of the forebulge. That then would be given by an expression like this. So the point is, we know how to calculate this. They're not terribly complicated expressions. They're a function of the physical properties of the plate, the thickness and the elastic moduli. Those come in then into the flexural rigidity, and that comes into the flexural parameter. Flexural rigidity is a function of the plate. The flexural parameter is a kind of ratio between the stiffness of the plate and the buoyancy force that's supporting it from below. This is what those solutions look like then as a function of the flexural rigidity. So the flexural rigidity is a big number. It's expressed in SI, which is Newton Pascal's. Oh, shoot, I don't remember what it is. Anyway, it's I'll have to check later. Anyway, it's a big number, 10 to the 22 to the 10 to the 25. It can get a few orders of magnitude. It varies by orders of magnitude and get a little smaller, a little bit bigger. But what's important here is that the shape and how that depends on the flexural rigidity. Higher the number, the stiffer the plate, the less the deflection, but the longer the wavelength of the deflection. So small flexural rigidity means that it sinks deeper under a load, but the width is much smaller. The amplitude of the peripheral bulge is higher. But these distances, for these numbers, are on the order of something between 50 kilometers and goes out to maybe 300 kilometers. And that would be, as I say, sort of typical values for a lithospheric plate. This kind of flexural depression goes out tens to hundreds of kilometers. Here's just sort of an example. This is the line load problem from Hawaii that I mentioned earlier. This is actually looking along that line now, though. So we're not going to quantify anything here yet. This is simply to show you that sort of what happens, what the physics of the situation are here. That we have a oceanic crust, oceanic lithosphere, and it's been loaded with this big mass of volcanic material that's been erupted on top of the surface. That's going to depress it. It's going to push it down, and that depression is then going to be supported by flexure. So if we look across instead of along this line, but we look across it, then what we have then is a lithosphere that's flexed down. There'll be a bulge on the sides. There'll be a moat, what we call a moat or a depression. This is the flexural depression that's next to the volcano, which is acting as the main driving load. So we have a big pile of basalt that's been erupted out here. And then we have this flexural depression around the sides. Now, one of the problems with working in the ocean is that the oceans tend to be full of sediments, especially when they have big islands sitting right next to them. So in fact, this infill, this moat here will be full of sediments, and that makes it hard to observe. So rather than, if you don't shoot seismic or something, you don't know where the top of the crust is. So the bathymetry will be pretty much flat. But what we can do for a quick estimate that's actually remarkably accurate is look at the gravity. If we measure the gravity along this profile, it will look like this. I'll show you some data in a little bit, but it'll look like this. It's going to have a gravity high due to the contrast between the rock and the water, but then it's going to have a gravity low on the side, which is due to the contrast between the sediment and the rock. So the sediment will be lower density, and that's going to cause it to go down. And the shape of this will mimic almost exactly the shape of the contact between the rock and the sediment until you get to here, and then it's going to really reflect the excess mass due to the island here. So gravity is a quick, easy way to see through the sediments and try to see where the support in the basement is really coming from. So here's some real data. Here's looking now at some depth data. This is not gravity, but depth, but this is the identified base of the sediments, if you'd like, the top of the oceanic crust, or the black points here. The bathymetry is the uppermost line here. So this is really the load of the island, if you'd like, here. But this is then the depression, the difference between the load, and this is the depression. And we can then try to fit that by guessing different flexural thicknesses and then a flexural rigidity, and then calculate this deflection curve. So here are a set of theoretical solutions for a lithosphere thickness of 10, 25, and 50 kilometers. And here's the fit to each of those, or the curve, the prediction for each of those thicknesses. And what you see is that for a thickness of about 25 kilometers, you can fit the data pretty well, right? Agreed? This goes right through most of the data through here. Of course, we don't know what's going on here, but it's a pretty good fit to that depression, that profile. And that would be our conclusion, that this is elastic flexure of the oceanic lithosphere with a thickness of about 25 kilometers. So here's just another picture, which is not Hawaii, but it's a similar setting, but has some nice seismic data, so we can see what exactly it is that we're looking at. This is Tenerife. We have an island here, a seamount. We have this flexural moat where with a bulge out here, and we can see then the sediments that are down in here, and see that that they are in fact flexed. They're going back up and down here, so there is in fact flexure going on, and it's that kind of fitting that we're looking at. If we go back to Hawaii, here's the kind of seismic data that are often used for this sort of calculation. Raw seismic data, the interpretation here, you can see the different reflectors that are the sediments, measure the tilt, measure the total deflection, or also measure the, or try to estimate what the tilting was at the time of deposition of an intermediate layer. So if you wanted to know, for example, is the flexural strength of the lithosphere changing with time, say maybe due to the volcanic heating, something like this, you could try to look at the time dependence of these sorts of things. All right, well, the second solution that we want to work with is the broken plate. So again, this is now looking at end loading of a plate where the other half is effectively gone. There's not continuity of stress between the two. Again, we can calculate this for different set of boundary conditions. There is a a W, this should say W max, I guess, because that's the, I'm worried here that I'm jumping, or this text is jumping between W0 and W max, so just be a little careful of that. But in any case, there's again a deflection, maximum deflection, exponential term, and a cosine term here. We again have an alpha, which is again the flexural rigidity term as defined before, or the flexural parameter is defined before, and everything is a function of x. Maximum deflection is a function of the load, and we can then get a solution like this now. Before there was a sine cosine term, now there's only a cosine, so it has a little different shape to it. And importantly now the flexure, the relationship for the, say, the width of the depression or the position of the maximum elevation on the bulge are somewhat different. And you can go back and look at the others to see how these vary. It's a little different shape, a little, and little bit different size for given flexural rigidity. But again, we can do the same sort of calibration exercise and say, okay, what's the shape of the ocean floor as it bends down into a trench? Try to find the flexural rigidity that best fits that form, and we might come up with something that looks like this. Again, these are real profiles, and we can get a nice fit to these. And what we find, in fact, is that there is some variation. In particular, there's variation in how rigid the lithosphere is, but almost all trenches have this kind of general form. It's been referred to as a universal flexural profile. That if you normalize everything by the flexural rigidity, then you can, in fact, explain the shape of much of these trench walls. One of the other predictions that comes out of this sort of a model, though, or this idea that we're flexing this, is that the stresses in the plate are going to be dominated by this flexural process. And in particular, as the plate is being bent through this outer rise down into the trench, remember that the stresses within the plate are in tension. It's a tensile stress in the top and compression in the bottom now, right? You can always look at the curvature and figure out kind of which way are you stretching it. But that's then the prediction is that this part of the plate should actually be under pretty strong tension. And in fact, we can verify that because we find that there are young normal faults found on this trench wall. So the deformation of the sediments of the surface of the ocean is in fact under horizontal tension, horizontal extension, and we're getting normal faults forming here. There are also earthquakes that show that in fact this is strong enough stress that that there are in fact normal fault earthquakes that are active as the plate bends down into the trench. Other sorts of observations that come out of this are things like little seamounts that are being carried towards the trench. If there's a seamount that actually comes up to the surface of the earth here, what happens to that? Well, it often gets dolotomized, or you get limestone reefs forming on the top of this that might be dolotomized, but they're at this point they're simply forming as reefs. But as this seamount moves with the plate over towards the bulge, it will in fact get uplifted. And this reef will then end up being like in this observation, this Niue Island. This has now been uplifted, so it's 40 to 80 meters above sea level. Okay, so that's significant. That's not sea level change, right? That's really uplift of this island. And then if we could continue to follow it, what we'd see is that it's going to then go down again back below sea level. All right, so how thick is the elastic lithosphere? What is the flexural rigidity of this, and what's controlling this? Well, in the oceans, everything's controlled by temperature, and everything is dominated by the fact that the oceanic lithosphere is formed at the ridge, and it's cooling off as it gets older and older. And the flexural rigidity is no different. So for example, maybe you've seen this sort of plot before. These are the depth of earthquakes in oceanic lithosphere, and what you can see is that they cluster, they group, but they tend to get the maximum depth tends to get shallower as we go towards the ridge. So this is age in this direction, and these are isotherms going up through 600, 750,000, and so on. And the earthquakes are by and large limited by a maximum temperature of about, say, 600 degrees, something like this. Now we can do the same sort of exercise and ask how the flexural thickness of the plate changes with the age of the oceanic lithosphere. We have to take this back to actually the time of loading. It's going to be important, not the modern age, but the age when a load was set on that lithosphere. And we find the same kind of relationship. In fact, there is, and these are all different studies of different ways of measuring the flexural rigidity, seamounts, trenches. There's some few cases of delta loading. You can also look at fracture zones and look at the flexure around a transform fracture zone transition. So all these are measurements then of the thickness of the elastic plate from the flexural rigidity. And what you find is that they're bounded by a temperature somewhere between 600 and 900 degrees, something like this. But it's a pretty good relationship. Now there's both of these have this slight problem in that if I were to ask you directly, what is the thickness of the lithosphere? I don't think anyone would, I hope you wouldn't answer that it's 25 kilometers thick, right? And yet that's exactly what we're sort of predicting here, is that it's up here. And if I were to ask you what is the temperature at the base of the lithosphere, I hope you would give me an answer something like 1300 degrees C. This is the asthenospheric temperature that is then defined by an adiabatic gradient going down through the mantle, but it's much, much higher temperatures and much thicker than these sorts of numbers. So what is that telling us? That's saying then that the elastic response or the elastic lithosphere is not the same thing as the thermal lithosphere. So this high temperature, this thermal is really defining the thermal boundary layer that defines the base of the thermal lithosphere, but the mechanical lithosphere, at least in response to surface loading, is much thinner. And it's actually, you can say the same thing about the earthquakes. There are not earthquakes occurring down in the deeper part of the oceanic lithosphere. So this is what this is telling us, is that this is really a rheological boundary within the lithosphere where we're able to support elastic stresses in the upper part, but not in the lower part. And the lower part of the lithosphere is deforming quickly enough that it cannot generate earthquakes and it cannot support surface loading. But the time dependence of this becomes quite important, and maybe we'll come back to that a little bit later. So here's sort of what that's, how we think this behaves, and I think you've seen these yield stress envelopes already, right? So you'd kind of have an idea of this, that we have a shallowest part of the lithosphere is controlled by brittle deformational mechanisms. It might be a Byerlee's law or a frictional slip on pre-existing fractures or something like that. And then we have a high temperature part of the lithosphere where we get temperature controlled creep. It acts viscously with ductile flow down here. The maximum strength is somehow in the middle. And to take this concept then to flexure, we have to also recognize, though, that the flexural stresses are not uniform, right? With depth through a plate. So this is a depth cross section TE here. Under flexure, we're going to have the maximum stresses at the top and bottom, and they're going to go through zero here. So if we take that kind of a stress field and we put it on top of a yield stress envelope like there on the right, we can in fact calculate, or at least estimate, where those stresses are going to intercept this yield stress envelope. All right, so if you remember these, we have to assume a strain rate in order to characteristic strain rate in order to calculate the bottom part. But if we do that, and it's asymmetric because it's it varies depending on tension or compression. But if we overlay that stress field on here, then we'll see that in fact it gets cut off at the top and it gets cut off at the bottom. And if we assume that we somehow have to support that surface load, what that really comes down to is that we have to maintain a certain bending moment. That bending moment is this M, and if we express that like this, it's an integral from the top to the bottom of the stress times the distance from the neutral core here. And so if we reckon, you kind of think of that as being the area under this curve, which is colored in orange, has to stay constant. And so you can calculate then what the stresses should look like for a given yield stress envelope. And if we do that, then we can start to, I'm going to go back 2 slides here. We can start to see or start to predict exactly what temperatures these stresses are no longer going to be maintained at here. Those are going to be relaxed and disappear. And what we're seeing here really then is this core of the yield stress envelope that's maintaining these bending stresses. Just one slide about the continents. Continents are a little more complicated because, of course, they're not necessarily dominated by slow cooling of material that was extruded at a ridge, right? So although this is looking at real data now, looking at the elastic thickness of continental lithosphere. It's plotted against the age of the continental lithosphere, which is already a very difficult thing to define because you can talk about the last orogeny or something, but it's very difficult to say there's an age to something with a complex history. And you can see that they're kind of a mess anyway. There might be a lower limit. If there is, it's probably at a lower temperature than the oceans even, but it's very hard to see much of anything here. And I think part of this is also the fact that the temperature is just not that uniform. Even if you knew the age of the last orogeny, it doesn't necessarily follow that the temperature and the geotherm are going to be a function of that age, because you have other things like radioactive heat production in the crust. So it depends on the crustal composition, the crustal thickness, and things like that. So even though we think there probably is the same kind of temperature dependence, and in fact these are going down to maximum thickness of 100, there are many examples where it's only 25 kilometers, 50 kilometers, and so on. So we think there is a temperature dependence, but it's much harder to pin down than in the oceans. All right, well, let me look at another, just a couple more quick kind of solutions to this problem that are sort of useful. And one of those is periodic loading of the surface. So if we have an elastic plate and we apply a periodic load, what might that be? Well, it might be, mountain ranges and valleys or something like that, right? It could be topography. That's really the best example. And but if we think about a perfect sine wave load that's applied to the surface, we can solve that problem too. And so we put that into our differential equation again, our 4th order differential equation. Now the load is a function of x, but it's still solvable. And in fact, what we find is that we get a response. So if we have a load that's this h of x, we can get a response to that, which is or we can calculate a load anyway, which is the f of x, which is just the rho g times this. And then we can calculate a response to that, which is this w of x. And what we find is that if the load is a sine wave with a particular wavelength, lambda, the response is the same thing. Okay, so even though we're now putting the periodic load on top of an elastic plate, we're not changing the wavelength of the response. And this kind of makes sense if you think about it a little bit, that if you have an infinite load, it's periodic, right? So it goes into x infinitely. You don't really know where you are. So on that signal, right? There is no plus and minus x or infinity other than relative to the wavelength. So you in fact can't be changing the wavelength, or you would be changing the phase, if you'd like to think of it that way. But so what it's really saying is that we have a different degree of compensation. So the W naught is different, right? Because that's a function of the flexure rigidity and so on. So the amplitude of the deflection is different depending on the flexure rigidity, but the wavelength does not change. And the other thing that comes out of this is that the wavelength, the W naught, the deflection, depends on the wavelength of the load. And again, the easiest way to think about this is to think of the extremes. If you have a very short wavelength, this W naught, in fact, goes to 0. So what that's saying is that if things go up and down very rapidly, you've got this, this periodic wave, it's going up and down quickly, it's not compensated. means that there's no deflection of the lithosphere. And of course, you think again about the extreme case. If you had a wavelength of 1 meter, it means it's going up and down every meter. The lithosphere is never going to feel that, right? Doesn't matter how big that load is. It's too small to be felt by the lithosphere. It cancels each other out from the positive to the negative. On the other hand, if the wavelength is very long, and this, I better have a look at this slide. There's something weird going on here. But if this one will be correct. If it's very long, what that's saying, this one is correct. If it's very long, there is local isostatic compensation. So the load will simply sink into the asthenosphere until it is exactly compensated, right? And that again kind of makes sense in that a very, very long load is not going to have an edge effect. There, we're not going to see this kind of flexural effect. And so we can kind of express that in terms of a ratio of this flexural to isostatic response. So what is the W naught compared to the local isostasy? When that goes to 1, that means it's fully locally compensated. When it's 0, then there's no compensation. And where the flexure is important then is in this region right here. Right. So and just to give you an idea, this is the kind of thing you should take home and think about it. But for a typical lithosphere with a flexural rigidity, there's my units finally, Newton meters. It was Newton meters, 10 to the 23rd Newton meters. That corresponds to about a 25-kilometer elastic thickness. The C here of 0.5 is achieved for a wavelength of about 400 kilometers. So if topography is loading with a wavelength of 1,000 kilometers, it's going to be locally compensated. And if it's loading the lithosphere with a wavelength of, say, 400 kilometers, 300, 200 kilometers, we're going to see flexural effects. That's where they're going to be important. If it's much, much shorter than 10 kilometers or something, it might not be compensated at all. But somewhere, in this middle region, then around these values, flexure is going to be important. Now, this is may seem like kind of a contrived example. Where do you ever have one sine wave of topography? But there's another very, very important characteristic of elastic flexure that makes this very important, this solution very important, and that's linearity. It's a linear process, and what that means is that these solutions add. And if you have the solution for one sine wave and then you add another sine wave on top of that, you can add the solutions to those two sine waves together, and that is the correct solution for the combination. Or if you want to do seamounts, you can put one seamount on an oceanic plate and then put another one nearby. Each of them has an elastic deflection. You can calculate the add those two elastic deflections together. That's the correct solution for the combined load. So that means that it's linear. That means that there's no secondary feedbacks or effects that they interfere with one another. And so what that means is that topography, even though topography never looks like a sine wave, it does look like a combination of sine waves. And you can do things like a Fourier series decomposition of any topographic field and write that topographic field in terms of a series of sine waves, solve each of those using this deflection, and you will get a valid solution. Or what's really done here is what we do in practice often, or things like the line load, is we can calculate the load due to a single block or a single seamount, whatever we're dealing with. Here's the solution. Here's block 1. We can do that for block 2. We might get a solution that looks like this. Block 3, block 4. All we have to do is add those up, and we'll end up with a total deflection curve that looks like the purple one. And there you can see, I hope, that how practical this becomes, because any topography, set of seamounts, any ice sheet, you can always do this. You can break it up into a set of blocks. You can make them smaller and smaller depending on what accuracy you want. Add them up, and you'll get the total solution. So this makes it really pretty straightforward to use these kinds of solutions. We can start to look at things like mountain belt loading of the lithosphere, where maybe we have here we have a lithospheric plate and we have a bunch of crustal rocks, say, that made a big orogenic belt. We have a foreland basin out in front that is filled with sedimentary rocks. If we add all of these things together, then we can come up with a single depression, the single flexural depression like this, put the load on top, and we'll have the surface topography. So I'll show some more examples in the next lecture, which is looking at some of the applications of this, but that's it for now. Thanks much.